Hi, and welcome to Temeko. In this video, we will take a deeper look into force vectors. We will establish how to represent force vectors with two different notations, which are scalar and Cartesian vector notation, after which we will go through the procedure of how to form coplanar force resultants using these notations. Let us get started. First thing that you may ask is, why do we need to use notation for representing force vectors? We usually resolve each force into its rectangular components, Fx and Fy, which are perpendicular to each other. The resultant of these two components is our force vector, F equals Fx plus Fy. For analytical calculations, we need to have a notation for representing these rectangular components. Let us start by establishing the scalar notation. Think about the planar coordinate system. It has an x and a y axis, which have both positive and negative directions and the magnitude. For this reason, we can define the rectangular components of the force vector using algebraic scalars. Depending on which direction the rectangular components are pointing in the planar coordinate system, they can be represented with either positive or negative scalars fx and fy. For example, if the component fx is pointing to the positive x direction and the component fy is pointing to the negative y direction, then the x component of the force vector is positive and the y component is negative. Just keep in mind that this scalar notation is only used for computational purposes and not for graphical figures. Let us move on to the Cartesian vector notation, which is very helpful for solving problems, especially in the three-dimensional cases. You may be thinking how this notation differs from the scalar notation. In Cartesian vector notation, we represent the x and y direction of the planar coordinate system with the Cartesian unit vectors I and j. The main property of the Cartesian unit vectors is that each unit vector has a dimensionless magnitude of 1, which makes them suitable for dictating the positive and negative direction of the x and y axis. If we use the previous example, which we used when establishing the scalar notation, then the force vector of that example can be described with Cartesian vector notation in such a form: F equals Fx times I minus Fy times j. Now that we have defined two notations to represent force vectors, let us see how to add force vectors together to form the resultant force vector. First thing that we'll do each time is to resolve each force vector into its components, and then the respective components are added together. After this, the resultant force vector can be defined by adding the resultant of the components by using the parallelogram law. For example, think about the following problem, in the planar case, in which we have three force vectors, F1, F2, and F3. If we use the Cartesian vector notation, then each of these forces can be represented as shown. Now, based on the resolved force components of each force, we can obtain the following force vector resultant Fr. If we could use a scalar notation to solve this problem, then by knowing that the positive x direction is right and the positive y direction is up, we'll have Frx equals F1x minus F2x plus F3x. Fry equals F1y plus F2y minus F3y, which are the same component resultants which we also got by using the Cartesian vector notation. So as you can see, we can generally say that the resultant components of any coplanar force can be represented as a summation of the components of all the forces as such. Frx equals summation of Fx. Fry equals summation of Fy. To calculate the magnitude of the resultant force vector, we use the Pythagorean theorem, which can be written, as you may already know, Fr equals square root of Frx squared plus Fry squared. We can also determine the orientation of the force by calculating the direction angle theta. Theta equals tan inverse Fry divided by Frx. In three-dimensional problems, we usually use Cartesian vector notation, in which case the resultant force vector can be written as follows. Fr equals summation of F equals summation of Fx times I plus summation of Fy times j plus summation of Fz times k. Notice that we added the k Cartesian unit vector into the equation to represent the z direction because this is a three-dimensional case. You can calculate the magnitude of the resultant force vector by using the same method as in the planar case, in which the squares of each component were summed up and then the positive square root was taken. To determine the direction angles for each component, you can use the following equations. Cos theta x equals frx divided by fr. Cos theta y equals fry divided by fr. Cos theta z equals frz divided by fr. Hopefully after watching this video, you know how force vectors can be represented by two different notations and how to also operate them to form the resultant force vector. Thanks for watching and have a nice day.